Today we're going to be talking about something that is not particularly exciting, but it's important, and you can think of it as differentiability. So the differentiability and algebraic operations. Some of this you've seen already in the previous sections. So let me first recall how we took the derivative of x to the sixth, right? How we took the derivative of x to the sixth, right? We had some function f of x was x to the sixth, and we wanted to calculate the derivative. So just remember, right? This was the limit of f of x plus h minus f of x over h as h approaches 0, right? And so that turned out to be the limit as h goes to 0 of x plus h to the sixth minus x to the sixth over h, right? Do people remember what happened then? What happened after that? What did we do after that? The what? You could use there's some formula, right? You can use Pascal's triangle, you can do something or other, right? It turned out that this was going to be the limit as h goes to 0 of x to the sixth plus, does anyone remember?
X to the fifth.
There's some x to the fifth h, there's some x to the fourth h squared terms, there's some x to the third h cubed term, there's some x squared h to the fourth, x h to the fifth, and there's an h to the sixth term, right? Right. So that's what happens to that thing, and then we subtracted off the x to the sixth, and then divided everything by h, right? And the important thing was the coefficient on this one. Does anyone remember the coefficient on this? You don't have to, but just in case you do. Joe?
Is it 6?
It's 6. Yeah, it was 6. It's 6. Right? And you've got some coefficients on these other guys. Okay, we don't have to worry too much about them because they vanish. But in case you do want to know, they were 15, 20, 15, 6, 1. Right. And then the 6's, x to the sixths canceled off, right? And then you see what happens, right? We got this h goes to 0, 6x to the fifth times h divided by h, right? So that's just 6x to the fifth, right? And then we have all these other things which have higher powers of h, right? H squared, h cubed, h to the fourth, h to the fifth, h to the sixth. When they're divided by h, well, you still have some power of h in them, right? You still have some power of h in them. And so this is going to be 15x fourth h times h. This is going to be 20x cubed h squared, et cetera, right? Each of these other terms, past this term here, all the other terms all have h's in them, right? And so when h goes to 0, then those guys, what happens to those guys? They all go to 0 too, right? So you get, each of these guys has some h in it, h times some other stuff. Right? And so when h goes to 0, this thing goes to 0, and you have to do 6x to the fifth. Right? And that's how we got the derivative of x to the sixth. And that's how one shows the power rule, which you've seen in the, right? That if you take the derivative of x to the n, where n is 0, 1, 2, 3, some natural number, then you're going to get n x to the n minus 1. Okay, so this is how one sees the power. This is one way of seeing the power rule. You have to go through. You could go through Pascal's triangle or whatever. But what's going to happen is basically the same thing as this. Same thing as this. You get x to the n plus n x to the n minus 1 h plus a bunch of other stuff that's multiplied by h, which vanishes. Okay, and so you're going to end up with n x to the n minus 1. Right, so in the general case, you get x plus h to the n minus x to the n over h. As h goes to 0, you get basically exactly the same thing is going to happen. X to the n plus n x to the n minus 1h plus a bunch of stuff multiplied by h minus x to the n, right? And then the x to the n's cancel, right? And, whoops, this will be h squared, sorry. So, and you end up with x and, you end up with n x to the n minus 1. So anyway, that's how the power, in case you were wondering why the power rule works, that's why the power rule works. Okay. Any questions about that? Any questions about that? Okay. Okay. So just remember, we've got this nice rule. You can take derivatives of monomials. These sorts of things are called monomials, like polynomials, monomials. Just one term of a polynomial. Okay. Or really, it's more appropriate to say polynomials are multiple monomials. Yeah.
Okay. Yeah, I was gonna say so if you have like a polynomial, you can take the individual monomial.
So technically speaking, we actually don't know that yet.
Okay.
So, but we'll get to it in 2 minutes.
Okay.
So yeah. So yeah, if to be a stickler, you don't know that yet. Okay. Yeah. So all we know at this point is how to differentiate monomials. Okay. Yeah. Okay. So then other things we have, right? So we've got the power rule. Other things we have are derivatives of sine. We saw that the derivative of the sine is the cosine, right? The derivative of the cosine, if you work it out, turns out to be negative sine, right? Okay. So those are other things that we've seen. Okay. And so these are the basic blocks for right now. Okay. These are like the blocks, and we're going to build out of these blocks. Okay. We're going to build on top of these blocks. Okay. Okay. So so that part is not the algebraic operations part. Now we're going to talk about the interaction with of differentiability and algebraic operations. Okay. Okay. So the first block is the first rule is simple. It says this: if you have some function f, a differentiable function, and alpha a number, right? Alpha some number. Okay. Then the derivative of alpha times the function is just going to be alpha times the derivative of that function. Okay, and you've probably seen this in the reading already, but let me just be systematic and lay things out systematically. Okay, so this is like application, right? If we are looking at 5 x to the 6th, right, and somebody says you want to differentiate that. Well, what this says is that you can pull the 5 out, right? You can say, well, I already know how to differentiate x to the 6th, so I'm allowed to pull the 5 out. Okay. I'm allowed what this says is that differentiation and multiplying by a number can be done in either order. They commute, right? This is a lot of our rules are like this and this commute. Okay. You can multiply by the number first and then differentiate, or you can you can differentiate first and then multiply the number afterwards. You get the same thing. Okay. And so this would be 5 times 6x to the 5th. In other words, 30x to the 5th. Okay. Right. And so that allows you to do a little bit more than just differentiating the pure monomials. You can now differentiate monomial multiplied by some number. Okay. So just to, and I'll hold on for 1 second. Okay. 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 The second thing is if you have f and g differentiable functions, then the derivative of the sum of these functions equals the sum of the derivatives of the functions. So how does differentiation interact with addition? Well, again, it commutes. It doesn't matter what order you do it in. You can take the sum first and then differentiate, or you can differentiate and then take the sum. So once you have that in combination with the previous one gives you the ability to differentiate polynomials, right? So like if somebody says, what about 6x to the fifth? Right, 6x to the fifth plus, say, pi x to the fourth. What's the derivative of that? You'd say, okay, well, I can just invoke my rules now, right? So I say, well, I'm not going to I'm going to do, instead of differentiating the sum, I'm going to sum the derivatives, right? So this would be this. Right? And then you would say, well, what can you do at this point? Not the power rule. I'd rather use the scalar multiple rule, actually. Right? Use the scalar multiple rule and say, I'm going to pull out the scalars. Right? And then at this point, I'd use the power rule, right? Right, so this is going to be 5x to the fourth plus pi 4x to the right? So 30x to the fourth plus 4 pi. Okay. So once you have these two guys plus the power rule, then you can differentiate all polynomials. Okay. Right. Okay. Yeah, Sharon.
Do you want us to show that most stuff on like homeworks and tests? Because like in my head, it's all just the same.
I know it's all the same, but at least I want you to be conscious of it. Okay. Because if you're not conscious of what rules you're using, then there'll come a point where you're like, can I do this or not? And you'll be like, I don't know. So be conscious of what assumptions or what things you're using when you actually use them, right? Because otherwise there will definitely come a point, and it won't be that far off from now, where you say, can I do this? Is this legal? And you'll have no idea if it's this. I see this a lot in people who come in into pre-calculus. Say they do things, and I say, well, what are you doing? Why are you doing that? And they say, isn't that true? Isn't that true? Okay, so even if you don't, be conscious of what rules you're using. Be conscious of what rules you're using. Okay. Okay. So yeah. So those rules. These are the rules that allow you to do that sort of thing. Okay? These are the rules that allow you to do that sort of thing. And just to give you a sense of why they work, why are these rules true? Why are these two rules true? It's actually pretty simple. It's actually very, very simple. So which one do you want to see? They're both equally trivial. Do you want to see scalar multiplication commutes with differentiation, or do you want to see addition commutes with differentiation? They're both like child's play. Multiplication. Okay. So okay. So y is so you have some function that is a multiple of another function. So scalar multiplication. One calls this scalar multiplication to distinguish it from multiplying by another function, right? Which is completely different. Okay, multiplying by another function we'll get to in a minute, but far more complicated, or somewhat more complicated. Okay, scalar multiplication. Right, y is g prime a times f prime. Okay, and let's just look at it. Well, g prime is what? That's the definition of the derivative. The limit as h goes to 0 of what? Well, it's too easy. What's the derivative? G of x plus h, g of x plus h, minus g of x over h, right? And so you say, okay, well, g of x, so let's just see what that is. G of x plus h is what? Alpha times f.
F prime, G prime over X.
What is g of you guys are panicking, I think. What is g of x plus h? G of x is alpha f of x. G of x plus h is?
Alpha.
Thank you. Thank you. Alpha f of x plus h. Right? And then g of x is alpha f of x. Right. Okay? Okay, right? Everyone all right with that? You've calmed down? Good. Good. Okay, and then you see what we can do. We can factor. We can say. We can factor. We can pull out the alpha, right? This is alpha. Right? This is alpha times that. That's just arithmetic, right? That's elementary school by your knowledge of elementary school arithmetic, right? And then what can we do? We can pull the alpha outside of the limit. Why can we do that? Because it's a limit theorem, right? We have this limit theorem how limit and arithmetic interact. The limit theorem says you can pull scalars out, right? So you can pull that out. Right? And you see what we're left with? We're left with f prime, right? Alpha f prime. Okay. Okay, so it's child's play, but maybe sort of old child's play. Right? You need to know what you can do and what you cannot do with limits. Right? Okay. So why is this true? Well, you just look at it. You say, well, this is going to be that. This by definition is that. This by elementary arithmetic, and then the key step that you can pull the alpha through the limit. Okay, alpha scale and multiplication, and taking a limit commutes, and then we're done. Okay, and same sort of argument holds for the sum one. Right, at some point you're going to use the fact that that the sum of limits is the limit of the sums. Okay. Okay, everyone okay? Any questions? Close your eyes for a second. Raise a finger if you're confused. Okay, open your eyes, please. Okay. Nobody is confused. Good. So why is that funny? I'm always up here thinking, trying to analyze what is funny to you guys. Why is that funny? That's just, okay. Okay, let's see. Okay. Okay, I'm just, we're going pretty fast, so let me let you do an exercise. Okay. This you have seen before, but I'm going to make you do it anyway. Okay. F of x is 1 over x. Take the derivative. Okay, so just take 1 minute and do that for exercise. Please do try it. Some of you are just sitting there. Maybe you already worked it out. Maybe you already worked it out quite recently. Okay, somebody tell me how to do it, or should I choose somebody randomly? Cynthia.
Well, why don't over x is equal to x to the negative 1.
Okay.
And then you can use the power rule and negative x.
Actually, you can't. Actually, you can't.
Okay, I take it back.
You can't. You can't. Why can't you? Why can't you? Why can't you use the power rule? Other than the fact that when I wrote it up, you remember, if you look at your notes right now, and you see when I wrote it up, I said n was 0, 1, 2, blah,
Okay.
blah.
Yeah.
Right? But why wouldn't what we did for the power rule work for this? Because we went through. What did we use to get the power rule? Pascal's triangle.
Okay.
Do you have a line for Pascal's triangle when n is negative 1?
No.
No, you don't, right? Do you have a line for Pascal's triangle when n is a half? Or any number other than, say, 1, 2, 3, etc.? No, you don't, right? So you can't, actually.
Okay.
Okay. So let's do it with our bare. Yeah, Richka.
Would it be natural law of x?
Let's work it out. So the limit as h goes to 0 of f of x plus h minus f of x over h, right? As h goes to 0, right? So what's that? F of x plus h is what?
1 over x plus h
1 over x plus h,
minus 1 over
right? Everything over h. H goes to 0, right? We can say find a common denominator on the top. So, right, you get x over x plus h minus x plus h over x plus h. Right, everything over h. Everything's divided by h, so I'm going to put in. Okay, I'll put an h right there for now. And then I'm going to combine it, right? So this minus that is going to be minus h over x plus h. And this is all divided by h, so I'm going to put an h on the bottom. Okay. Right, you can see what happens, right? The h's cancel out, right? And you get negative 1 over x squared plus xh minus h goes to 0. Right? And so you get negative 1 over x squared. Okay. Okay. Which is, as some people are muttering, exactly what you would get if you use the power rule. So that makes you suspect, maybe, that the power rule works for negative numbers? Maybe. Does it work for irrational numbers? Rational numbers? Does it work for all numbers? Does it work for complex numbers? Okay, so later on we'll see that the answer is yes. Okay, but you see that we don't. There are things you know and things that you actually don't know, right? Pascal's triangle, you needed to get the power rule. Pascal's triangle doesn't have a row for negative numbers, for fractions, etc., etc. So be conscious of your knowledge. Be conscious of your knowledge, right? Otherwise you will misapply it. You'll misapply it. Don't be sloppy with your knowledge. Don't be sloppy with your knowledge. Okay, that's the moral. Because otherwise you'll definitely misapply it in a very simple case, and maybe even in more significant, serious cases. Nothing's going to happen to you too bad if you misapply some rule. Although something very bad could happen, like you could lose your job, say, if your job depended on this sort of thing. Like the people who some years ago there was a satellite sent to Mars and it crashed, right? And you remember why the reason? Because they didn't convert from the English measurement system to the metric measurement system, right? the satellite crashed. Millions of dollars, hundreds of millions of dollars wasted. So anyway, be conscious. Don't be sloppy with your knowledge. I wonder what happened to the person who did that. Right. His or her head is probably on a pole somewhere, as a warning to others. Yes, Alfred.
So are we not allowed to use negative numbers for the problem, or?
You can use it for -1. You can use it for -1, and if you look in your book, you see that they use it for -1 only. Yeah, only at this point. Yeah. Although it's true, and I think in this section they maybe starting from this section, they say, in fact, it's true for all real numbers. In fact, it's all true for all real numbers, and feel free to use it from this point on. However, we're not going to explain it until a couple of sections later, because to explain it requires something we'll get in the next section. Okay, so right now what we have is interaction with scalar multiplication and sums, right? Okay. Right. And this allows us to do, so we can do what are called linear combinations of functions. Right, that's like, you can do 5x to the 5th plus, 6 times sine x. Some sort of combination that uses only sums and multiplying by numbers. These things are called linear combinations. Okay. We don't know at this point about multiplication of functions. Just multiplication. Like if somebody says, what's the derivative of the sine times the cosine? Okay. What's the derivative of the sine of the cosine? At this point, we don't know. Okay. But we'll give it to you right now. So there's a formula called the product rule, or also called Leibniz's rule. That says that if f and g are differentiable at some point, if f and g are differentiable at c, then the product is also, f times g is also. And the derivative of the product at that point is going to be the first guy's derivative, well, probably some of you know it already. What is it? The derivative of a product, Ellie?
The derivative of the first times the second, and plus the derivative of the second.
Derivative of the second times the first. I'm gonna write it like this: the derivative of the first times the second plus the first times the derivative of the second. It's the same thing for you guys, but it'll actually be important later on that the order is preserved. When you get to Calc 3, then you'll have to keep it in order. So I'm going to keep it in order now. Okay. So for example, if you're taking the derivative of this product here, right, we're going to use the product rule. So for example, if we take the derivative of the sine times the cosine, you get the derivative of the first guy, right? The derivative of the first guy, which is the cosine, times the second guy, plus the first guy times the derivative of the second guy. Okay, so you get cosine squared minus sine squared. Okay, or if somebody asked you for, say, the derivative of three things multiply it by each other. Take 1 minute and try this, please. Take 1 minute. You have to basically do this in an iterated manner. Or I guess we've already done part of the iteration for you. Okay, somebody tell me what to do, even if you haven't finished it yet. Somebody tell me what to do. Arichka.
Well, so we're going to go by the power product rule.
Yes.
So you first are going to start with 2x, which is f prime.
Okay.
And then you multiply that by sine x times cosine x.
Okay, so you're splitting it like this. You're saying, I'm going to take the derivative of this guy times that guy. So I'm going to take the derivative of x squared and multiply that by sine x cosine x. Right? And then I'm going to add on.
The derivative of sine x cosine x, which you saw above.
Okay, so we're going to get this, the function times the derivative of the other. Right? The first guy times the derivative of the second guy. I'm sorry, the derivative of the first times the second plus the first times the derivative of the second. Okay. Right. That is to say, we take the derivative of the first guy times the second guy plus the first guy times the derivative of the second guy. Okay. Okay. And if we hadn't worked this out before, then we simply have to work it out now. Okay. That is, you'd use the power rule twice. Okay. And notice that there's a choice involved here. Right? We could have said, I'm going to take the derivative, I'm going to call this thing the first guy and this thing the second guy. Right? That could have also happened. So I'm going to take the derivative of the first guy times the second guy. So, or the derivative of the first guy times the second guy plus the first guy times the derivative of the second guy, which is negative 1. And that will end up with the same thing anyway. Okay. So there's some choice involved, and we'd have to use the chain, we'd have to use the rule here, the product rule here again. Okay. Any questions? Any questions? Okay. I'm going to erase this. Is that all right? I'm going to erase this time. Let me sketch out why this works. Why should we believe this? Why is this true? Why is Leibniz's rule true? Right? Because most people, when they first see this, if you ask somebody who hasn't seen differentiation before, what's the derivative of a product? They often say, shouldn't that be the product of the derivatives? They're hoping that you can commute, right? They're hoping that, oh yeah, the derivative of the product is the product of the derivatives. Doesn't matter which order, right? But in fact, that's not what happens. Differentiation and multiplication don't commute. Instead, you have this sort of funny rule, okay? So, let's think. If I look at the derivative of this product. What do I write on the right hand side? The limit as x reaches to 0 of what? Somebody just say it to me for me.
F of x plus h.
F of x plus h.
C plus h.
F of c plus h? Okay, sure.
Minus f of c. Over h. Now sine of
Be careful, be careful. Right.
FG.
This, we're taking the derivative of f times g. Right? This is our function, f times g. Right? So over here, it should be f times g. Right? We're differentiating that function, not f. It looked like you were taking the derivative of f independently.
Yeah.
Right? So let's be careful. Right, so this will be f times g evaluated at c plus h minus f times g divided by c, everything over h. Okay. Don't worry. Good to be bold. Okay. I mentioned the rule of shamelessness, right? Have I mentioned the rule of shamelessness? No? Okay. Yes. Right. This is said to me by my Chinese teacher in college, and he said, the rule of the rule of learning is shamelessness. Right? He said, I hope that all of you can basically, like, children learn because they have no shame. Right? They just speak and they get correction. Right? And that's the way they do it. Right. I assume I've told you the related story where I get stopped as a spy. Yes. Okay. Very good. Sorry, I can't keep track of my stories, and I just use the same stories every year. Okay. Okay. So what do we get? We get the limit as h goes to 0 of f of c plus h times g of c plus h minus f of c times g of c. Right? Just by definition. Right? And then you think, okay, how am I going to find where's, right? Look at where we're trying to get, right? We're trying to get to this thing, right? It doesn't look like, are we getting there? Are we getting there? Okay. Doesn't look like it, but at this point we're going to play a trick, okay? We're going to play a trick, and that trick is to add on 0. So we're going to add on 0, but it's going to be a very funny looking 0. This I don't expect you to come up with. I'm just going to show it to you. Okay? We add on 0. There it is. We subtracted something and we added something. Exactly the same thing. That's 0. Okay? Adding on cleverly chosen 0 is often done. Is often helpful. Or multiplying by a cleverly chosen 1. Okay. Okay. So maybe this is starting to look a little better. Maybe this is starting to look a little better. What happens to it? I'm going to break it up into pieces. F of c plus h minus g of c plus h minus f of c g of c plus h over h, and then I've got this thing, which goes to 0, f of c, g of c plus h minus f of c. Okay, and here we're using the fact that a limit of the sums is the sum of the limits. As long as the limits exist, and we'll see in a second that they do exist. Yeah, Helen.
Can you go over adding the zeros? I'm not quite sure how you got.
So I just look at the difference between this line and this line. The difference is the two circled terms. And you see that the two circle terms are opposite of each other. Right? So I've added on 0. Okay. Okay. What is this? What is this? Does anyone recognize it yet? F of c, g of c plus h minus f of c, g of c, everything over h.
Oh, derivative of G.
Derivative of g times f of c. Right? You can pull out the scalar f of c, and we get left with the derivative of g. Things are looking better, right? Things are looking good, right? And what about this thing here? This one will need to be a little bit careful. The limit as h goes to 0 of, I'm going to factor out, over there I factor out the f of c. Here I can factor out the g of c plus h. Right? I've got the f of c plus h minus f of c over h. Right? Okay. What happens to this thing? The derivative of f at c. What happens to this thing? As h goes to 0, this goes to g of c. Right. So you get g of c times f times c plus f of c g times c, which is what you wanted. Okay. Now, just to be a stickler, I'll say that we have to be a little cautious when we do this. We're actually using the fact that g is differentiable and thus it is continuous. We use the continuity here, otherwise this is not going to happen. When h goes to 0, you don't know that you end up with g of c. But g is differentiable, so it's going to be continuous. Okay? So this actually does work. Okay. Yeah, Alfred.
When you write it out, would you rearrange the order so that it's f times c times g of c for the final and c? Because you said like order
First.
Okay. Yeah, sure. I can rewrite it like this. Yeah. At this point, yeah. Sure. Okay, the last rule is the so-called quotient rule, right? The interaction of differentiation and division. Okay, so questions? Questions? People are singing. People are chanting already. Right, the quotient rule, right? If you have f and g differentiable at c, and g at c is non-zero, then the quotient is differentiable at c with the derivative with the derivative being the bottom times the derivative of the top. Oops. Bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom die squared. So to make this concrete, if I take the derivative of the tangent function, right, the derivative of the tangent is a quotient, right? And so we end up with the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom square. right? And so that ends up being 1, right? You get cosine squared plus sine squared on the top, 1 over cosine squared, in other words, aka secant squared. Right? So, right, this is just a rule. Again, we could prove it basically by using some tricks. We can see why this is true, just as we saw as the multiplication was true. But I'm not gonna do it. Just take. You can look in your book to see how it's done if you like. Yeah.
Sorry, how'd you get from cosine? How'd you get that? The last thing?
This?
Yeah. Mhm.
So right here we've got cosine squared, right? Cosine squared plus sine squared, which is 1, right? Right, which is 1. Okay, so we have 1 over cosine squared, in other words, secant squared. Okay, so maybe take a minute and try this one. X sine x over x plus sine x. And take its derivative. And I'll start passing back some papers. Michelle? Okay, so what do you get? You get the bottom, right? And then the bottom times the derivative of the top. What's the derivative of the top?
Sine x.
What's the derivative of the top? It's not just sine x. Right? You need to use the product rule on it. So you get the first times the derivative of the second plus the derivative of the first times the second times the second. Right, by the product rule. Bottom times the derivative of the top minus the top times the derivative of the bottom. What's the derivative of the bottom? 1 minus cosine x, right? Using the linear. Sorry, plus over the bottom square. Okay. Any questions?
We need to figure out if that's like simplifiable or.
No, that's plenty. This, if you do it to here, it indicates to me that you know the quotient rule, the product rule, and the interaction with the plus, with everything else. So.